the Downtown Line 2 project in Singapore was built over the last 7 years. What we're looking at here is a concourse platform level on one of the stations called King Albert Park. The thing about metro programs that I think is really important to bear in mind is that if you look up the definition of a metro, it says a large population area of adjacent zone of influence. You can also look it up and you'll see a definition that says metro rail transport, a railway system in an urban environment with the capacity and high frequency for delivering people from place to place. So the corollary here is that the adage of bring it and the people will come is certainly not true with metros, because those people need to be moved around efficiently, and the point being that they actually in the most already exist. So most metros around the world you are building inside existing urban landscapes. So what is required to deliver a metro program? Certainly complex works in an urban environment. Public and stakeholder management requirements, multidisciplined delivery methods. There will be disruption. What we're trying to do though is to create an end user facility that is efficient, it has disabled access, tactile structures, and it's a pay for use program. So it's got to be an appealing product for the end user, not just for the people who actually build it. So in the talk tonight, what I'd like to step through is Singapore's their metro network and their plans for the next 15 years, the key elements of building an underground metro program, the design and construction approaches we typically adopted, some key aspects of managing risk, definitely some lessons learned. I think that's a pretty critical one to discuss, and the final outcomes or the final product and what did we actually achieve after what was essentially 4.5 years of work. I've got a picture up here. I mean, I think it's important when we consider engineers and engineering, we have preconceptions of what we do and what the world thinks of us, and these are the typical images you get off the web. Young men wearing ties and suits and hard hats. I couldn't even find a gender equality picture on the web, which I found interesting. But I think the main thing is, as engineers, we are decision makers. And when you think about it, what we actually do is we do one of two key things. I think we make people's lives improved, and we actually make people more mobile. And when you think about the engineering fraternity, that's probably the two key things we do. But I think more importantly, the engineering industry is about listening and communicating. If we are an industry that wants to achieve best practice and engage in knowledge learning, I think communicating and sharing is actually the way forward for the industry. So hopefully that's what I'm here to do tonight. I guess you'll be the judge of that. Hopefully I get the key messages out. It's very hard to get the balance between the detail versus the overarching themes of what's important in metro construction. Singapore. I'm sure quite a few of us have been there. It's a very industrious and prosperous part of the world. GDP of $85,000 per person per annum. So it's right up there with the tax havens and the oil nations. It is a place that is putting a big investment into its transport system in the metro space. DTL2 is the red line, runs through the heart of Singapore. Importantly, and I'll come to this later in the presentation, the centre of the island's on granite. They call it Bukatima granite, is the local name for it. And then overarching that granite is this layer of fluvials and alluvials and soils. And as of course happens with metro programs, our tunnelling horizon, you guessed it, was right along the interface of those two strata. So here's the wider metro of Singapore. The blue line through the middle of the page there is the Downtown Line 2. The section we built was from Beauty World, which you can see on the blue line there, through to the 6th Avenue station. So we built 3 stations, and we built 5 kilometres of tunnel between those stations. Just to give you an idea of the metro program coming up for Singapore, they've got a current daily ridership of around 3 million. They're targeting 5 by 2030. The system underground right now is 190 kilometres. It is intended to reach 400 kilometres by 2030. That'll be larger than the London Underground network. The main lines that are yet to go in will be a downtown line 3, which you can see in the brown, completing the circle line, and there'll be a cross island line and a number of other lines. And that program will roll out over the next 15 years. Just some minor details on the track systems. It's all standard gauge. Most of the stations are below ground. They are what they call civil defence shelters. So they can, in foreign hostile invasion, these stations are designed to sustain aerial attack and bombardment, and they become a place of refuge. The stations are air conditioned, as are the trains, and all the trains are typically 6 carriages, DC 750 volt, third wheel propulsion, and they're all automated. So every train in Singapore is driverless. So downtown line 2 delivery schedule, 7 years in the making. There were 10 D&C contracts for the delivery of the downtown line 2 for the stations and the tunnels, and there were 2 major M&E and line-wide system contracts. So the packaging that we were engaged with was for a D&C model. We delivered 3 full stations, 5 kilometres of tunnel, and by a full station this included all the utilities, traffic diversions, temporary works, excavation and construction of stations, building works, architectural works, full requirement to space-proof and future-proof for M&E, and full coordination responsibilities for the M&E and line-wide systems. In the driven tunnels, we did the tunnels, the cross passages, the track bed, the cable brackets, and ventilation and power supply for the line-wide systems. So, metros under construction. I think the important thing is that there will be disruption, but our objective in building a metro has to be to ensure that we continue the existing services as much as possible. Metros will go 24/7, and in the slide alone you can start to get an indication of some of the necessary traffic diversions to take place. You can see the disused road here, and already there's a new traffic diversion in place which is fairly well frequented. So looking at traffic diversions for a moment. What's not important here is the detail behind the sequencing. What is important here is the green outline is the station footprint. There was Bukatima Road right through the middle of that station, and if you've been to Singapore, Bukatima Road is a major arterial through the heart of the island. So the important aspect here is that the staging and sequencing that's required to build a metro station needs to ensure all utilities are diverted, you can complete the station box, all the stakeholders are managed, and that the subsequent work can proceed without restriction. The original road will be moved 10 times in this next sequence. So the stages 1 to 4 on your screen, stages 4 to 8, all the utilities and piling are going on. I'll show some slides later. And lastly, stages 9 and 10. So to actually create an environment where you can actually build a station under an existing road takes an enormous amount of traffic diversion, and we haven't yet started building a station. So this is probably fairly well illustrated in this slide here. Most of those traffic diversions had to occur as indicated in the first 18 months of the project. I think a couple of key points that I'll mention around traffic diversions is that first of all they're a bit of a misnomer. All works for traffic diversions are designed to a permanent road standard. I think the second one is the rigorous review process you've got to go through, or we need to go through. They are fully designed roads. We had third-party review of all our traffic diversions, Government Safety Department review, LTA Safety Committee review, and then we carried out full audits after every traffic diversion was activated to ensure all signage was compliant. And we also had to station people on major corners. There will always be confusion after a traffic diversion. So to make sure that even bus drivers, commuters, the general public understand the new requirements is critical. When we create these station boxes, what we've actually got to achieve is to develop a underground retaining structure so the station can be completed. In Singapore they call this an ERSS, and it's the excavated retained safety structure. So that is your temporary works to build the box. Typically D-walls, secant piles, sheet piles are used. We used, in this particular station, we used secant pile wall with secondary grouting. There was a cut-off of 3 metres into the host rock, about 20 metres below the surface, and there was a major recharge well. So settlement control is very critical on these stations. We've got alluvials over the top of granites, as I've indicated. All the buildings on, that is the southern side you're looking at, they're all old masonry structures with literally within 5 metres of the secant pile wall. On the southern side, which you can't see yet, all buildings on friction piles. So control of the understanding and control of the geology, the hydrogeology and settlement control is extremely important. Utilities are always an aspect with urban structures. This picture gives you an idea of the requirements. Singapore rainfall is pretty famous. On the surface of the existing road network was a 5 by 4 metre reinforced concrete box culvert. We had to relocate that, transfer that water into these two large twin 2 metre diameter pipes, and we had to undersling that under the decking on the station, insert it on rails to achieve that utility diversion. I think the critical aspects for utilities for us were, and what we learnt was a few things. Full-time utility engineers. They sound obvious, it is important. The up-to-date maintenance of your drawings and the control process for your notice to commence excavation, a control process for your licensed cable detection, inspections and permit to dig. Utilities are about approvals and planning, and they are also about process control. And I think my final point about utilities, which I'll come to in the lessons learnt, would be to say it can be very easily underestimated, the risk to a project on the delivery impacts for failing to address what can go wrong in delaying utilities. So now an aerial shot. So again, what we're looking at here is Bukatima Road, which ran through the middle of that station, has been probably by now relocated half a dozen times. We've got the road running over the top of the station. We've got buildings on friction piles on this side. You can start to see the formation of a launch box at the top of the project. You can't see it very well there. I'll talk about that later. But I think importantly, you can see the proximity of the stakeholders. The large building in the top right is what they call a housing development block, houses about 8,000 people, and a multitude of stakeholders around. There's wet markets under those trees. So the urban environment is certainly on top of you. I think the key thing with stakeholders that we learnt were do the basics well, and the processes typically look after themselves, but certainly early engagement, a consistent message. This was a multi-package delivery, so a consistent message from the parties, the contractors, the client is important, and deliver to what you say you will do. Interestingly, blasting. We did a lot of blasting in Singapore. This is Bukatima granite, 200 MPa, and what we actually found on the project was that with the right processes and indicating to the public that there will be sirens and warning and pamphlet and information around how to control the blasting and what will happen was very well received, as opposed to endless hours of mechanised rock breaking. So once a day at 4 o'clock there'd be a siren, there'd be a blast, and within 2 weeks of commencing that activity, everyone was going about their business as if blasting was just part of their common day. So our objective here is to end up with a situation such as this. Controlled access points, a fully decked out station. That traffic you can see is running on decking. The work is occurring underneath, unknown to the public. There's minimal disruption and a full and proper delineation between the public and the work site. Again, another shot. The shot you just saw was down from here. This is now access points up the station, launch shaft up in the top of the picture. So what's going on down below though is interesting, that most of these stations are either top down or bottom up. I think the important aspect is that they all require significant engineering inputs to sustain ground loads, maintain a watertight structure, maintain traffic loads, and enable access from above for all the critical works that are going to continue throughout the typically 2.5 years that you're going to build one of these stations. So then we put it all together. We've got tunnelling. You can see the shield being assembled down the bottom of the picture for the TBM. You've got station excavation occurring right all through the centre of the picture. There's traffic diversions going on, there's piling, there's utilities diversions, and what we actually have created is a very busy construction site in an urban environment. And we typically do it 24 hours a day to achieve program. You've seen a lot of pictures and probably trying to piece together what does a station actually comprise. This is one of the 3 stations we built. This is called Beauty World Station on account of the shopping centre above it called Beauty World. The major elements probably will be, there's the footprint of the station itself. So we've got a crossover tunnel on the left, trains can switch sides. The main station platform concourse is in the red footprint here. It's particularly wide in the throat of the station because of the civil defence requirement. So that station under a threat or invasion can actually house in isolation about 250 people. It actually also has filtering systems for decontamination in a nuclear event. You also see the launch shaft separated from the main station to delineate the interface for launching the TBMs, and importantly these entrances A, B and C. And these are significant structures, and importantly entrance C, it's almost 400 metres of underground structure, so that you saw in the previous photographs the housing development blocks and the markets, so the access can be attained from the entrance C all the way into the concourse level. And that was almost some 400 metres from the entrance point down to the concourse. And lastly, the RCBC that we saw as a utility, that we had to use those twin pipes underneath the station, that you can now see where it existed prior to us commencing the station. These station constructions, people talk about top down, people talk about bottom up. What does it really mean? The truth is there's an element of each of these requirements when you build one of these stations. So your sequences are to build the retaining structure, the ERSS, by piling. You then, as you excavate down, you install struts. You can see the first layer, S1 strutting going in here. You'll install decking. That'll subsequently be driven on, or plant and equipment will be placed on it. And then you'll excavate to depth, and then you'll do bottom up. So from the bottom, you'll start your reinforced concrete works, and as you come back to the surface, those struts will be removed. We had 5 layers of strutting on the way to the bottom of the station, and underneath the underlying S5 strut, about another 7 metres to the final formation level of the station floor. So a couple of things on strutting, particularly in the Singapore environment. The king posts, which are the major columns you can see in the middle of the picture, they do take the horizontal strutting loads, and if at all possible, my recommendation is to avoid them. Your piling around the perimeter goes to rock level with a 3 metre cut into the rock horizon, but king posts must travel to the formation level of the station, so they can be very expensive and time consuming to instruct. There's the redundancy requirement. So in Singapore, if there is a strut failure, a single strut failure, the system must be able to withstand that strut failure and stay complete. The critical element also with strutting is the monitoring and instrumentation. So all of these struts on the critical elements had real-time monitoring with TARPs, trigger action response plans, and web-based systems with alerts. So tunnelling, a lot of data up there around our particular TBMs. It's all important. We did EPB and slurry TBMs, 2 of each, so 4 in total. All the parameters are important in terms of an engineering perspective, but I think the one that's pretty critical is the soil conditioning. It's not probably given sometimes the focus that it needs, and I think with soil conditioning, particularly in the cutter head, it's got to be effective. I mean, it's got to work. It's got to be flexible because the geology changes, and it's got to be robust. It's got to last the distance. But we're engineers, so that was a factory acceptance test you saw in the previous slide. So no sooner do we take a perfectly functioning operational TBM, but we pull it all apart, put it on a ship and send it somewhere and practice putting it together again. And here's the machine going together in Singapore in a couple of slides. In the launch box, getting close to final assembly. The TBMs were named Athena and Artemis in a local schools competition. We call them the green and the blue TBM. And this is the geology they travelled through. So just very briefly, you can see an indication of the tunnel alignment through that geology. But I think the thing that I'll say here is beware the blue line. So the blue line is the indicated rock horizon. So 200 MPa Bukatima granite, above it alluvials, fluvials and very easily mobilised soils. Now, Booker Tema granite's great for your kitchen bench top, and alluvials are completely the opposite. In the ideal world, what you do here is you tunnel through a full face of rock and you have a TBM that's specified for that. Or in the ideal world, you tunnel through a full face of soil and your TBM's specified for that. But we're in a metro environment, and often is the case, you are travelling along a horizon that is dictated by station depth, fire life safety, alignment of track. And our alignment, as you can see, skims right along that mixed face horizon. Very briefly on geological considerations with mixed face tunnelling, it really is about your planned interventions to coincide as much as possible with good geology. Problems you typically occur when you have unplanned interventions, and unplanned interventions, they typically occur when your spoil conditioning system is failing. A slide here which is not a lot of tunnelling going on, but what I'm trying to illustrate here is, I think this is somewhere off a UK moor. And if you imagine that blue line was on the previous slide, it was indicated by the bedrock. And on that interface, you will always get large mobile boulders. And if you imagine a TBM coming from the left or coming from the right and driving right along their horizon, if you don't have your systems correct, you can imagine some of these large boulders becoming very mobile, and you can imagine the result of those boulders becoming very mobile when you are only 15 metres below the traffic horizon. So a picture that a lot of us will have seen before. I think the key thing that I want to say about TBM designs is that you get all the basic parameters right. There's a lot of experience from designers, from the suppliers, from contractors around the major engineering parameters, and we typically do get them correct. The soil conditioning aspects are incredibly important. If you get them wrong, they can cause clogging, overheating, excessive wear, major overflows from the screw, or arching over the screw, or ultimately machine failure. People love this stuff. They write books about it. What can I say? Maybe the original would be a better read, I think. But again, I stress that the key points are, the mitigations are: know your geology, engineer your TBM to that geology, and have the skills to adapt to a changing geology. But ultimately, you persevere, you end up with a long, straight tunnel under construction. You can see slurry pipes on the right-hand wall, temporary rail running through, that's for tunnel construction. That's all come out now. You can see now first stage concrete, ready for handover, cable brackets in place, and you can see now that's final track, ready for power systems. So a bit of performance here. On the left, we've got the performance of the slurry TBM. On the right, EPB. This is monthly progress. This is aggregate. Pretty simple chart. But before we rush off and decide that everyone wants an EPB, just remember that if the EPB was working in the geology that this machine worked in and vice versa, they would both fail. I think the other one to note is that this machine worked in about a 70% horizon of mixed face. This machine worked in a horizon of mostly soil, which occurred later in the program, so you can see the dramatic increase in productivity. And this machine here also worked 24/7 as a result of the client requiring us to accelerate and deliver the program early by about 4 months, which we achieved. So interfaces, they are everywhere on these metro programs. You've got TBMs coming into a station, you've got TBMs going out of a launched shaft on a station. You have the reinforced concrete works, the building works, the architectural works, you have the mech and elect rooms, you have line-wide system access. This launch shaft also served as a line-wide system for the rail system, so from that point they went several kilometres in both directions. There's signalling requirements, HVAC, fire life safety. So managing all these interfaces is pretty critical. TBMs coming into stations, you can do it a couple of ways. We did it in a numerous way. This is a photograph showing dock and dismantle. So in this photograph, the TBM has arrived into the downstream station. We've now docked. We're now going to strip the TBM, which is going on at the moment, and the shield will remain in place, and that'll form the former for the permanent lining. Or you can drive the machine through the diaphragm wall or the second pile wall, whatever it is, and do a knockdown and take the TBM out of the station. They both work. There's no right or wrong. I think the key elements are, the alignment. When I say the alignment, the physical alignment between these interfaces, the wriggle surveys, the kinematic envelopes, they are important. There's interfaces in the station. This is a station build going on. There's architecture, there's plant rooms, there's HVAC. You can see some escalators there in the picture. There are several ways to set up metros for optimised program delivery, and none are perfect. And ultimately, the job always needs to be completed. I think the key principles are probably what matter, and the ones that I've listed here, which I think are important, are clear contractual requirements, clear defined dates for access, defined windows for specialised activities, have a dedicated coordinated integration program, CIP we called it, and have a defined program owner. Whether that is the client, the contractor, or a third party is irrelevant, but it needs to be assigned. I think avoid wholesale blending of disciplines. It may de-risk some interface, but with the right approach, the right tools and the right people, these challenges of interface are always manageable. Risk management itself, as the slide indicates, what industry tends to try and do is transfer it, manage it, or insure it. So what is best practice risk management? Everyone's got their own view, there's mine. But I think the requirement is that when you look at history, it does suggest that a lot of risks, and potentially half of them, are identified post-award. So having a life cycle of risk management processes in your job is the key, where those risks are identified and managed. I think the other thing that I'd add is that the well-managed, well-identified risks are never the issue. It's more the ones that take you by surprise. And I think the other element about risk management is that ultimately, and what's sometimes not appreciated, is that there'll be decisions to manage risk around a price and a safety outcome. There'll be change to methods, there'll be changes to design, there'll be engineering controls, and there'll be a price and risk outcome. So best practice in my mind is really about getting the right people in the room with the right attitude and setting up good tools of communication to make the right decisions. So lessons learned. What did we do well? What do we learn from? As I said, I think with utilities and diversions, it can be the most underappreciated risk to a project is utility diversion and approvals. I think the key lessons for us will be focus on your planning and your sequencing, have dedicated utility staff, and I think wherever possible, clients should actually initiate that approval process. Ultimately, someone will need to take it over, but it needs to be initiated as early as possible to avoid delay. I think the other thing that we learned on access was a real focus on the stakeholders who you don't typically think of. Maybe we should, around the elderly, special needs and wheelchair. We did make a reasonable attempt at this. We got better at it, but really to set it up for success, you've got to make a dedicated effort to not just to have the right process and plan in place, but to actually have the follow through with people on the ground to ensure that everyone understands what is required under the new traffic management or diversion once it's activated. Another lesson learnt would be BIM. At each station, we typically installed about up to 40,000 linear metres of services of various kinds. Everyone thinks about BIM potentially in the permanent space. We did adopt some BIM. We could have done so much more with BIM. I think the other one, this is some reinforced concrete work in the underground station environment. So with BIM again, temporary work systems, proprietary systems, space compatibility with BIM, this can save you a lot of delay and disruption. More about BIM. Often when we think about space proofing, we think about have we got enough space? Clearly, there's plenty of space here. And I think with BIM, you can avoid situations like this where you do overcompensate. Cross passages. Cross passages can often be located on drawings that suit fire life safety requirements, as opposed to where they might be geologically best located. So cross passages can be very disruptive to a program. Put them in the best spot you can within the constraints of fire life safety. They are complex, and they can take a lot longer to install if they're incorrectly positioned on an alignment. Waterproofing. Tunnels, some pretty well engineered solution for ring building with segments and gaskets, no problem. Stations are pretty well engineered for waterproof structures, and we are in a metro rail environment, it needs to be waterproof. The critical areas we found were that structural interfaces, penetrations and construction joints and concretes are where you focus your attention on, because you'll do the proprietary systems very well, but those three areas are where you'll need to revisit. Just the next few slides here, I've got half a dozen slides on what the final product looked like and what we actually achieved. So I like to try and step through from the surface to the underground and give you a few pictures of what it looked like along the way. So these overpasses, very grand and very, I think, quite attractive. Here's a picture from inside. This is another overpass we did. Escalators. I think the architecture and the finishings there are very good. That's a shot from another angle. So certainly the integration of the entrances with busways, taxi stands, and overpass to traffic utilities and bus stands and taxis on the other side of the road was done particularly well. Cycle stands. This is entrance A, if you remember the slide showing the station that you saw on the footprint. And these entrances, they were intended to be notable, and they took actually inspiration from the Bukatima Hill nearby. So they do look large and impressive, and it was certainly an intent of the client. Here's another shot from the opposite view, similar theme. You can see also the linkway coming out of the picture to the left. And this is now entrance C. If you remember that long structure that came away from one of the stations we built, a lot of effort's gone into the architecture and the finishings here. There's tactile, if you can pick this up, this is tactile flooring for the vision impaired. And turnstiles, I think the important observation we made here was that the safety campaign poners on behalf of the client were very well done, very highly visible in the trains and in the station. The operating system made very frequent announcements to passengers, commuters waiting for trains, and it was all extremely well communicated to the public. This is now a shot of the concourse level and the platform at a lower level. Obviously disabled access is very well catered for. This is another station. This is called King Albert Park Station. Again, a lot of tactile in the architecture, a few creature comforts for people waiting for trains, and platform screen doors on the platforms. I mean, platform screen doors, they're installed on all the stations. They're often thought of as safety to prevent suicides, but they actually also enable climate control in stations, and they do restrict unauthorised access. And of course, what those trains run in is almost a final shot of the running tunnels. Just needs the cables and the third rail to be installed, and that'll be ready for a train. So commissioning actually started in late January of 2015. This was the very first train to run down our section of line. The person in the foreground here is Sim Wee Ming. He was Director of Transport for the LTA, a very happy gent. And behind him was Kee Nam. He was our project director for our delivery program. So from January 15 through to grand opening, we're now in December of just last year, and we've now got a fully operating DTL2 in Singapore. So that's the end. I hope I sort of, without getting lost in the detail, covered what I think are some of the key aspects of delivering metro programs. They are complex, they are urban, but there are always solutions. So thank you.